Thank you for introducing me. Good afternoon, everyone. My name is Minsik from KISTI. KISTI is a national supercomputing center in South Korea. I'm working in the supercomputing infrastructure center, whose main role is deployment, operation, and user support of HPC system. So first, I want to introduce our new system called Nurion, whose name was decided via public participations in naming contest. It means, in Korean words, enabling as many people as possible to use this machine. So, as the National Supercomputing Center, KISTI provides computing resource to Korean researchers and engineers from universities, government, and industry since 1988. In 2018, we support more than 800 projects and 2,500 users and help them to use our machine for their research and development, and publish more than 200 SSI papers in last year. So this slide shows the overall history of our current system, KISTIi, which is called Nurion. We began our project by constructing new building in 2015, and we started to provide service from 2018 December. So KISTIi system is one of the largest cluster system in the world. It composes of about 8,300 KNL nodes and 132 Skylake nodes, which are connected by OPA interconnect. Each night landing node has 68 cores and 96 gigabyte DDR memory. It also has 16 gigabyte size HBM, which is a high bandwidth memory. The CPU only memory node has 2 Skylake processors and 192 gigabytes of main memory each. Also, we have a parallel storage system of KISTIi. The amount of parallel file system storage is more than 220 petabytes, equipped by DDN exascaler. It also has NVMe type burst buffer, which is around 3 times faster than DDR storage. And the computing node and storage are connected by OPA interconnect. It is a 2x1 blocking factory topology. So in this slide, more detailed connecting about OPA is represented. So in our system, we run several benchmarks for the performance evaluation, which is HPL, HPCD, or Graph 500 and IO 500. And through these benchmarks have successfully run on huge number of KNL and Skylake nodes. It shows indirectly the system reliability and stability. We provide several queues with various node configurations to support users. Since most computing nodes of our system use Intel KNL, one of the configuration options is the usage of HBM. In flat queue, HBM is used as a scratchpad memory, which is called can be allocated data by user defined. Otherwise, HBM is used as a L3 cache with a direct map cache structure. Also, we provide long queue and exclusive queue to support, which requires longer than 2 days. About 6 months since the production started in December 2008, systems CPU usages are getting higher and now reaches about 70%. The one of the thing different from previous system is user drop size. In the previous system, average drop size of around 100 to 20 CPU cores now is more than 2,000. Since the system opened, we started providing singularity image for machine learning framework under our drop scheduler. 5% of our user drops until now has used this image for their applications, and also we try to support more than. Next, I will present the performance test result on Nurion supercomputer. So currently, we aim to support large-scale jobs with improved performance. We have two goals: determine the configuration to achieve high performance and to minimize the performance variability. So first, we tune the MPI parameters in MVAPICH2 on our Nurion supercomputer. After that, we evaluate the performance on two benchmarks which have similar characterizations to the user applications. Also, we evaluate the performance of 3 applications which requires large-scale system. So first, we tune the parameter for the performance of collective algorithms of MVAPICH2 on Nurion supercomputer. These figures represent latency of the collective algorithm with small size messages. The performance of collective communication shows similar as its scale. In the MPI altogether, Intel MPI slightly better performance than MVAPICH in large scale. Also, MVAPICH shows better performance on MPI Auto in large scale, and otherwise it shows similar performance. And first we tune the parameter and we try to evaluate our performance on several benchmarks. One of the benchmarks is HPCG. HPCG has 4 types of workloads, and each workload there are only communications. So we for the evaluation we use 8,000 nodes before the preventative maintenance. So before the node reboot, we try to evaluate. And 32 open MP threads are used for evaluation, and process per node is 2. So there are 16,000 MPI processes, and we use the optimized code for Intel Xeon Phi processor, and all of those use cache mode. So in the performance evaluation, MVAPICH 2.3 is faster than Intel MPI on dot product and sum of 2 scaled vectors, and similar performance on sparse matrix, vector multiplications, and multigrid preconditioner. And Intel MPI is faster than MVAPICH on all these. So overall, there are similar performance, and it's very heavily influenced by memory system performance. So after that, we try to evaluate on after the reboot system reboot. So, but in cache mode of KNL system, KNL memory bandwidth performance has been degraded as lapse of the time after reboot. So even we try to node clear, like such as join sort, drop cache, or anything else, and it's not enough. So, in the figure, first when we reboot system, it shows a slightly low performance, and after the node clear, it's almost optimized performance. But every time we run the HPCG application, and system is slightly slow than before, and it's not it is very problem. So we add the reboot policy based on the stream benchmark result, and after that we do the performance evaluation. So second benchmark is MPB. These benchmarks are derived from computational fluid dynamics applications. So for the evaluation, we use 600, about 600 to 3,800 nodes in normal queue. So it's basically use cache mode, and we use problem class F, which is the largest problem class in the MPB benchmark. So for the evaluation, we use one OpenMP thread, and each node for 64 processors. So about 246,000 MPI processors are used for evaluation. So in the performance evaluation, Intel MPI faster than MVAPICH BT, which is a block tri-diagonal solver benchmark. And in the Scala penta-diagonal solver is a very similar performance. And in the LU, which is a lower upper Gauss-Seidel solver, MVAPICH is faster than Intel MPI. So also in the performance evaluation, MVAPICH shows better performance on the large number of nodes. And second one is performance evaluation about variation. So we use 676 nodes in normal queue, and this is smaller than before evaluation. And for the performance variation, we repeatedly perform 10 times for each experiment. So in the block BT, there's a similar performance, but also MVAPICH shows less performance variation compared to Intel MPI, and otherwise also same performance variation. And after that, we evaluate on user applications. The first application is DNS TBL. It's direct numerical simulation about the turbulent boundary layer. So in this code, this is the optimized code for Intel Xeon Phi processor, and this is optimized by KISTI. So for this is evaluation, 64 node to 512 nodes in normal queue are used for evaluation, and 8 OpenMP threads are used for each process. So processors for nodes are 8. On this application, Intel MPI is so faster than MVAPICH2 on velocity and pressure solver, and MVAPICH is faster than Intel MPI on update velocity and pressures and others. So overall is very similar performance. And second one application is a GOT-PM, which is a grade of octree particle mesh. So it's application of astrophysics and it's embodied simulation. This is a hybrid scheme that using particle mesh for long range first, and after that this application use a tree-based method for force correction for short range. And also we use 640 nodes in normal queue. And in this case, we use 64 OpenMP thread. And so process per node is 1. In the TSC and for the FFT and trade correction, there are similar performance, and Intel MPI is faster than MVAPICH on Poisson equation and backward FFT, and MVAPICH faster than Intel MPI or other computations. So in overall, it also similar performance. And last one is LAMS, which is a large-scale atomic molecular massively parallel simulator. So it also fixed version of the code, and it's we changed the initialized part by the 3D hollow instead of link communication pattern. So it basically didn't affect the output. And for evaluation, for 256 nodes are used for small scale evaluation, and 128 to 2048 nodes are used for large scale evaluation on normal queue. So also one OpenMP thread are used, and each node there are 64 processors. So all this case, MVAPICH is faster than Intel MPI on both cases. So we analyze this result, and there are a very large performance gap between MVAPICH and Intel MPI on K-space and neighbor. In both cases, there are MPI. They use all-to-all communication. So because of this, MVAPICH is much faster than Intel MPI. So in conclusion, we evaluate several benchmarks and applications. So it depends on the application communication pattern, and also it depends on the size of problem and number of nodes. So find the best configuration is basically depends on the application and size of problem and number of nodes. And also we our desired feature of MVAPICH2 is runtime auto-tuning for collective algorithms, because we use a job scheduler, and every time job scheduler cannot configure the same configuration. So we should every time to optimize we need it. So also the tuning parameters for factory topology are our desired feature, because performance variation between intra-rack and inter-rack is very different. So in the graph, inter-rack configuration requires almost more than 10% for broadcast and reduce. And this is also shows performance gap to the usual applications. And if the job size is large, allocating node by job scheduler shows also there are performance variation. So when our system is not busy, like first case, allocating nodes are very dense distributed. But when our system is very busy, allocating nodes are very sparse distributed. So there shows a very performance degradation with sparse distributed. So we used for this case we use MVAPICH2 default option, and there are performance degradation occurred by alter communication and altogether. So tuning parameters for topology is highly required. Yeah, thank you.